So I think we left off yesterday in the middle of a problem, did we not? We're working on this guy, yeah? So find the points on a curve where the tangent line is horizontal or vertical. So this is kind of like the last set of problems you guys have to do. These problems, they're going to show up on the WebAssign. And then the areas between curves as well as arc length, I think might be on the last WebAssign, as well as like the last three problems on the written homework for this week.
I have a quick question.
Yeah.
It's about the content, but what's the best way to pick your I guess theta values? Because that's the one thing I've been noticing I'm struggling with. Because I get random values and then it becomes difficult to graph it. So I didn't know if there's a certain way to pick like theta values.
It depends on the functions you're seeing. For one, like since we're graphing in polar coordinates, let me see. I kind of threw away the notes, but yesterday I kind of drew our coordinate system. It'd be like the coordinate system if we're looking down at the North Pole, right? Where we have these concentric circles and then the radial rings. And so the radial lines are your values of theta. The values of theta you want to choose have to be you. I would recommend picking nice values of theta that are on the unit circle. We teach the unit circle from pre-calc and beyond, mainly because those are the values that we know and can compute. So multiples of pi over 4, multiples of pi over 6, multiples of pi over 2. Those are going to be the best values of theta. I always like to choose multiples of pi over 4. Seems to kind of give me an easy enough idea. Start at 0, go 45 degrees, 45 degrees, and then kind of see where the graph is at based off of that. And in most of these polar coordinates, a lot of them at least, the equations are going to involve some sort of trig functions. So you want to be able to evaluate those trig functions. And so you want to pick nice values that we know and love and can compute from the unit circle. And if you can't, like there's certain graphs, I think we did one where it was like r equals theta. That one, of course, you're picking values of theta, even if they're on the unit circle. You still want to pick the unit circle values, but now computing, the actual radius. If the radius is pi over 4, you just got to estimate those. And for most of those types of problems, if you're just matching a graph, that's the key point. You really want to just be able to like estimate it. You don't have to really draw precisely accurate values for your distances.
Okay, that makes a lot more sense. Thank you.
So we've got our graph of r squared equals sine of 2 theta. And now our goal is to find the horizontal or vertical tangent lines. And so just like with parametrizations, we're going to have a horizontal tangent line. Really want to think of it, what is a horizontal tangent line? It means we're not changing vertically. It just means dy is equal to 0. And in this case, since we're parametrizing everything with respect to theta, so our horizontal tangent lines are going to be where dy d theta is 0. Likewise, our vertical tangent lines, the x value isn't changing, going straight up and down. So that's going to be where dx d theta is equal to 0. So let me actually rewrite this. We're going to use these notions a lot. So I actually just want to solve these in terms of our differentials. We have our equations x equals r cosine theta and y equals r sine theta. So these are our defining equations converting polar coordinates into rectilinear coordinates. And again, just like we were doing with trig subs and u subs, if this is my x, we can take a dx by taking a derivative of this guy. We do just want to remember that r is a function of theta. So we get dr d theta cosine theta plus r sine theta, and so r negative sine theta, that should be a minus there, times d theta. And of course, if we wanted to, we could sort of divide by the d theta to get dx d theta equal to that equation. Do the same thing with our y's. Our dy is going to be dr d theta sine theta plus r cosine theta d theta. And so from that, we really just have to fill in the values. We're working with r squared is sine of 2 theta. So we may want to compute the pieces individually, namely dr d theta. We can do that implicitly or explicitly. It is going to be a little weird. We got to be careful with that squared term. So if we take a derivative of both sides, this will give us a 2r dr d theta. It's going to give us 2 cosine of theta, cosine of 2 theta. And so our dr d theta is going to be cosine of 2 theta over r. So I'm just trying to think of how we want to go about solving this. I kind of want to keep it in this form. There's a couple ways we could. If we wanted to, we could try to solve this equation for r. Of course, if we do so, we're going to get a plus or minus, right? We'll have plus or minus square root of sine 2 theta. And having the plus or minus is a little sketchy. We can't just keep track of it with our work and with our algebra. Or we can simply, for now, leave our dr d theta as an implicit function. So when we fill this in, we are going to have our dx d theta is going to be dr d theta and then minus, we'll keep all the r's as they are. So we're not substituting in r as a function just yet. We might have to. And so if this is our dx d theta, we want to know where that is equal to 0. So when our rate of change of x is 0, this gives us our vertical tangent lines. So let's see what happens if we can solve this out. I'm kind of not liking the fact that our arguments are different. So we might actually have to expand that cosine of 2 theta. One of the things we can show, so when we're setting this equal to 0, of course, we're going to have cosine of 2 theta. Let me just rewrite it. Cosine of theta minus r sine theta. This term is over r, and we're setting that equal to 0. If we find a common denominator, put r squared over r, so multiply the right term by r over r. And now with a common denominator, essentially both of those have r in the denominator. This does imply that we don't want r to ever be 0. So r itself can never be 0, which is fine. The equation in the numerator is going to give us our cosine 2 theta minus r squared sine theta equals 0. We could have arrived at something similar with our pluses and minuses in solving for r. Again, do just want to warn you to be a little careful with the pluses and minuses. And nicely enough, when we worked it out this way, we did get this factor of r squared in there. And now that is how our polar equation was written. So we're going to have a cosine 2 theta cosine theta minus sine 2 theta sine theta equals 0. So now making that substitution in for r squared worked out in this case. And so now we have to solve this guy. We've got cosines and sines. Unfortunately, it does not look like anything can factor. You could try to eyeball and guess what values of theta, but even that with such expressions looks a little tricky. So let's go ahead and keep doing the algebra, breaking things down further and further. Our cosine of 2 theta and sine of 2 theta, let's go ahead and use the double angle identities. Cosine of 2 theta is cosine squared theta minus sine squared theta. And then we've got that times a factor of cosine minus sine of 2 theta, 2 sine theta cosine theta, times sine theta. Collecting our like terms, we've got a cube, which is typically not a nice trig function. Sine squared theta cosine theta minus 2 sine squared theta cosine theta. So hopefully some things will cancel, and then maybe we can do some factoring to simplify our lives a bit. So I guess not cancel, but combine there. Did I get all the minus signs right? That should be a negative. That should be a negative. So it is a minus 3. Okay, so we've got cosine cubed theta minus 3 sine squared cosine equals 0. So factoring out our cosine theta, and then we've got cosine squared minus sine squared equals 0. So all in all, that seems to simplify down quite a bit. And now, of course, cosine squared minus sine squared theta. We can then recombine the cosine of 2 theta if we want, or you could solve it from there. So I'll give you guys a second. Everyone caught up with writing?
What happened to the 3?
It disappeared, it looks like. That 3 should be on this guy, right? Good. Thank you. Missing my constants. Okay, so now we can't use the double angle formula, I guess. Anyway, that term is not going to be too hard to solve. So it'll be easy enough to solve it in there as it is in terms of tangents. So let's keep going. So product of two terms, we were going to have our cosine theta equals 0, and then we're going to have our cosine squared theta minus 3 sine squared theta equals 0. This guy, got to remember way back in pre-calc and hopefully in calc, you guys got some more experience with this. How do we solve our trig identities and trig equations, especially equal to 0? So this one should be theta is equal to odd multiples of pi over 2. Now that we know a bit more about sequences in series, We know that this is going to give us odd numbers. And then odd multiples of pi over 2. So 3 pi over 2, 5 pi over 2, 7 pi over 2. And of course, the negative values as well. Excuse me. And then this guy, so we're going to have cosine squared theta equals 3 sine squared theta. And let's see, let's solve for tangent, because no one really likes cotangent, right? Tangent is clearly the better one. So we will have 1/3 is equal to tangent squared theta. Tan theta, be careful with your squared terms. Anytime you're applying a square root yourself, include that plus or minus. So for that, you got to remember your unit circle. Of course, we've got that square root of 3. So our reference angle is going to be pi over 6. So for this guy, our theta is going to be every multiple of pi over 6. Since we don't care whether it's positive or negative, we need the first quadrant, second quadrant, third quadrant, tangent's going to be positive again, fourth quadrant, back to negative. But since we want both to be positives and negatives, what are we going to get? We're going to have all reference angles of pi over 6. So we'll have pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. Of course, we can include the negative values as well. And since we're in Calc 2, let's go ahead and actually write these as sequences. So anyone understand or kind of see how we can write this as a sequence? It's actually easier if we write it as 2 sequences. We kind of want to keep these terms together and then these terms together. So what's the next one going to be? Next one's going to be 13, right? So we'll have pi, we'll have 1, 7, 13. Those increase by 6 each time. So we're going to have 6k plus 1 times pi over 6. And then the other sequence is going to be 6k plus 5 times pi over 6. So here when k is 0, that'll give us our 5. Of course, the next one's 13. And then what's the one after that? Going to be not 15, 17. So of course the distance between 5, 11 is 6. The next one will be 17 for that one. So those are our points. And of course, because this loop is going to keep going around and around and around, which is why we find essentially there's infinitely many times when we have a vertical tangent line. Let's suppose we actually just want these specific values. It's going to be enough to simply do one full loop. Meaning, if we want just between 0 and 2 pi, maybe we can pick out those values. So what are we going to have from our first solution? We're going to have 3 pi over 2 and, sorry, pi over 2 and 3 pi over 2. And of course, beyond that will be bigger than 2 pi. With these ones here, we're going to have our pi over 6, our 5 pi over 6, our 7 pi over 6, and 11 pi over 6. So if we go back to our drawing may not be the best. Let's try to pick these out. we saw it like pi over 4, that should kind of go through where the tip of that pedal is. So if we go less than that, if we're somewhere down here at pi over 6, probably be a better point of tangency where the vertical tangent line is. And then we're going to go around, and where's the next vertical tangent line? Pi over 2. So at the angles vertical, you can see the curve is coming down, and we'll have a straight vertical tangent line. Then the next one, we actually have 5 pi over 6. So we might have found some extraneous solutions here, maybe coming from this tangent function with all these squareds that are going on. Because 5 pi over 6 is going to be over here. So let's check a few of these. So if we check five pi over 6, we're going to have our equation, r squared is equal to sine of 2 times that. And so r squared equals sine of 5 pi over 3. And what's sine of 5 pi over 3? It's going to be a pi over 3 reference angle in the fourth quadrant. So sine of 5 pi over 3 is
negative root 3 over 2.
Yeah.
Negative root 3 over 2, yep.
Yep. And so it does not exist. I was mentioning this yesterday, that we might see some extraneous solutions, especially with these squared functions. So anytime we get an angle that is in the third quadrant, it's not going to work. So we can throw that guy out. And then likewise, angles in the fourth quadrant, we should also find something similar. So if we check 11 pi over 6, what's going to happen? That's going to say r squared is sine of 11 pi over 3. So 11 pi over 3 is the same angle, same reference angle as 5 pi over 3. So if you just take 11 pi over 3 minus 6 pi over 3, so minus 2 pi, will give us 5 pi over 3, and that'll give us the same thing. So this guy doesn't exist either. Theoretically, if we were over the complex numbers, maybe we could make arguments for that. But that would be our solution set. So our vertical tangent lines at, let's list them in order, pi over 6, pi over 2, 3 pi over 2. No, sorry, 7 pi over 6 comes next, right, if we were listening in order. 7 pi over 6, and then 3 pi over 2. Now, if we wanted to actually find the points, we could simply plug in these values into our cosine theta and our sine theta. So if we needed to find xy coordinates, plug in your thetas, and then you would also then plug in your thetas to this equation to figure out what your r needs to be. We should also note that these are kind of symmetric in some sense. So if we were solving for the r's, again, we're going to have a plus or minus because of that squared. But it shouldn't matter, because if this guy here is at pi over 6, 7 pi over 6 is exactly opposite. It's on that same line. So while we found the vertical tangent line here, it makes sense that the same vertical tangent line is on the opposite side by symmetry. So even though pi over 6 will have that one theta value, we'll solve it for two r values, a positive and negative, but those will also correspond to the same vertical tangent line at 7 pi over 6. And of course, a similar thing is going on with pi over 2 and 3 pi over 2. Any questions on that? Do you guys want to see the horizontal tangent lines? Essentially the same process. We just got to take dy d theta and set it equal to 0. I don't want to spend too much time on it if we don't have to, though. Let's go ahead and move on. Maybe we can come back to this if you guys want to see it worked out. I'd rather do some more problems, especially because we want to get into areas in arc length and see some examples with that. So let's start with areas. Areas is the harder one. Not much harder. Actually, the integrals might even be easier, but it is like at least a new kind of theory behind it. And because when we have a graph in polar coordinates, we're measuring the distance from the center. You want to think of a particle moving around, typically moving around counterclockwise. And the distance from the center, of course, is going to be measured by the radius. So it could start to come around. And as we saw with some of these hearts, sometimes it loops up and down. Sometimes it comes in and then makes a hump. And we're kind of just measuring how much the radius changes as we're rotating around the circle. And so if we want to measure like a specific area of it, let's say we want to measure that green area just in the first quadrant, what we need to do is come up with an area element that corresponds with our coordinate system. So far we've done areas, all of the slices and the way we break things down. When we're doing rectilinear coordinates, we're making rectangles. It's actually why we call it rectilinear coordinates. Of course, Cartesian, our other term for that. But we've also seen that now when we have these volumes and surfaces of revolutions, well, now our volume element, our differential in terms of the volume, satisfies these formulas based off of the area of circles, the areas of cylindrical shells, and all that kind of stuff. So we want to kind of change the geometric rate or the geometric shape in which we're measuring our area element. And so what we do, let's say we take a look at like one little slice here, and in some tiny increments, since theta is typically our independent variable, and so that is what we want to increment in an infinitesimal manner. Namely, we want to think of blowing this up, and the curve in a small angle, say d theta, it's going to be mostly a circle, or at least using a circle to approximate that section of the curve, going to be very close. No, you guys are not going to have to derive this whole thing on the exam. So let's get to our formula here quickly. So of course, our area elements, the areas we want to add up, are these slices of pizza. And you kind of just have to remember, hopefully from pre-calc where you guys learned this, that the area of a sector is going to be 1/2 r squared times the angle. So the area of a slice of pizza. Of course, if the slice of pizza is the whole pizza, namely the angle is 2 pi, we get our well-known and loved formula for the area of a circle, pi r squared. So it's always a good mental check to check those constants if you're getting them right. And so this is kind of all there is. This is our area element. Of course, our radius isn't changing. If we wanted to be really precise, there might be some slight dr because the curve isn't necessarily precisely a circle. But in higher math, you kind of show that that falls off like a second order differential, and it actually doesn't contribute to the area. So that's kind of all there is. The rest is just using that formula and doing the work with these polar equations and really trying to figure out what areas we're finding. So let's do some examples. I can actually do you guys a solid. Maybe we can work through one of the homework problems. I was looking through some of the problems in the book, and one of them is very kind of classic example, very similar to what you guys are going to be doing in the homework. We'll start off with something different just to get warmed up. So let's find the area of one leaf of the clover. So clover is going to be given by R is cosine 2 theta. If you guys haven't yet practiced any of the graphs or matching graphs, again, highly encourage you guys to take a look at those and simply practice graphing like as soon as you can, because you want to be able to understand the graphs of all of these polar coordinates before you're doing the calculus. It makes doing the calculus much more smoothly, so that way you don't make mistakes on the graph and understanding what the function is. So let's plot it real quick. It tells us that it's a clover. Let's try to make sense of why. We've got our theta and our r's. So again, I like to increment our thetas just by pi over 4. Go up to pi and then see what's going to happen. So our radius is going to start out, cosine of 0 is 0, or sorry, 1. I was actually looking, yeah, we don't want to scale that or anything. So it looks like the scale on our graph is just going to be out to 1. At pi over 4, we're going to get 0. So because we're multiplying the angle by 2, you may even almost want to cut the angles in half if you really wanted to. Pi over 8 to pi over 4, since we're doubling the rate of speed with which we're traversing the circle, so to speak, with that factor of 2. But if we just compute these r's, what's going to happen? We're going to get alternating between 0 and 1 and -1. So let's graph it. I'll use my green for our lines. So when the angle is 0, we're pointing horizontally. We go a distance of 1. When the angle is pi over 4, we're at the origin. When the angle is 2 pi, or excuse me, pi over 2, so we're looking vertically here, but the radius is -1. So we actually go in the opposite direction and we're down here. So because the points are getting a little out of order, maybe we start to sketch those first 3 points just so we're kind of following the path. We started here, and if we start here and we're rotating counterclockwise, I have to rotate counterclockwise, but we're also shrinking down to 0 as soon as we get to pi over 4. So another way you can kind of think of how to draw these, on this line of pi over 4, the curve is going to be essentially tangent to that as we approach that specific point. And then what's going to happen, I should be pointing vertically, but now I'm going in a negative direction. So this is going to go from 0 and then decrease negatively. So even though the angle is going from this direction, we're looking this direction, but we're going negative. So we're actually kind of going in the opposite direction down to there. So this is how these things are traversed. And then what's going to happen, we go back to 0. And again, it's weird because we're at 3 pi over 4. So we're pointing upward. We're rotating around counterclockwise till we're pointing in 3 pi over 4. But because we're going from now -1, we're increasing, but we're still negative up until we get back to 0. So we're going to kind of come up this way. And again, at this point, we'll kind of be pointing now in that direction of 3 pi over 4. So that gives us our first loop. And then we're back at 0. And then at pi, our radius is 1. So pi, of course, we are facing left. And then the radius goes to 1. And so we loop around and we'll be there. So hopefully you can kind of get an idea of how this is going to be traversed. If we were to keep going, the next value is going to be 0, and we'd be pointing this way. So we're coming in and we're decreasing to 0. So we're going to be pointing in the opposite direction. Then we're going to come up, hit the vertical loop, come down, and then close off the clover leaf. And so now we're in a little bit of a conundrum, because you've really got to understand how this thing was traversed. And it's a little weird because when we started at 0, we go all the way around, but then we start on this first petal, right, on the right, but then the curve then goes down to the bottom petal. We complete the bottom petal, go to the left petal, complete the left petal to the top petal, and then complete the right at the very end. So it just tasks us with finding the area of one leaf of the clover. Any ideas of how we should do this? We just say angle, let's say angle ranges that define one leaf of the clover. Right? This is just kind of like determining the bounds of integration. So the integral, not too bad. We can go ahead and set that up. Our area is just the integral of dA. So the integral of 1/2 r squared d theta. R squared is going to give us cosine squared 2 theta d theta. Easy part to set up for the integral. Just plug in our function to our formula. But what are the bounds? We got to be careful because we want the bounds to encompass one leaf. A lot of different ways to do it. You want to be careful starting at 0, because if we go like 0 to pi over 2, it would kind of be like this top half of the leaf and then this half of the leaf. You could go instead from minus pi over 4 to pi over 4. That would actually start when we're pointing downward here and coming this way around through 0 and then up to that pi over 4. You could pick any other range as well. You could go from pi over 4 to 3 pi over 4, essentially any consecutive values that go from the 0 back to the 0 would work. Or we could just double the integral. So if we go from 0 to pi over 4, so 0 starts here, and you want to think of the area being traversed radially. So draw from the origin, if you kind of like to make these lines, and shade radially. So we start off going from at angle of 0, and then when our angle increases, that's kind of how we shade. So if I were shading from 0 to pi over 4, we see that we just get that top half of one of the petals. By symmetry, though, we could just double that. So let's go ahead and do that. It'll make our lives maybe a little easier. Of course, we're still going to have to integrate cosine squared. So just going to be 2 times 1/2 from 0 to pi over 4 cosine squared 2 theta d theta. So you got to remember how to do cosine squared. Cosine squared is 1 plus, let's write it as 1/2 plus 1/2 cosine of now 4 theta. So 1 plus cosine 2 theta all over 2. Of course, since we started with an angle of 2 theta, we go to 4 theta. We're integrating from 0 to pi over 4. And so what are we going to get? We'll get 1/2 times theta plus 1/8 times sine 4 theta. And then evaluate 0 to pi over 4. So we'll get pi over 8 plus 1/8. Sine of pi, just going to give us 0. And of course, when we evaluate at 0, we'll get 0. So we just get pi over 8. This is going to be the size of our clover leaves.
Can you go back to the other page real quick? Cool, thank you.
Let's do at least one more of these. So yeah, and these ones, the area ones in particular, I think are where the graphing skills are going to come into play, because it really helps you find the bounds of these. Let's see, where's my outline? I think you guys have one on the homework. Looks similar to the ones I was going to do. So homework says inside both, r equals 1 plus sine theta and r equals 5 sine theta. So with polar coordinates, because things are defined by this theta, you always kind of want to imagine them wrapping around the center. There's always going to be a clear inside and outside. So inside, we mean closer to the origin, outside, away from the origin. We're going to have some graphing to do. Let's call this R1 and R2. So here's our theta. Let's go our R1, our R2. So 0, pi over 4, pi over 2, 3 pi over 4, pi. 0, we got 1. And here we got 0. Pi over 4, 1 plus root 2 over 2. And then 5 root 2 over 2. Pi over 2, we got 2. Well, 5 there. 3 pi over 4, 1 plus root 2 over 2 again. And then 5 root 2 over 2. pi, we're back at 1, and back at 0. Let's draw R1 in green. So I think we actually drew this guy yesterday, or at least something similar. And then since our biggest value is going to be about 2, oh no, we've got to go out to 5. Maybe we need a bigger axis, at least vertically. So R1 is going to be at 1. At pi over 2, it's going to be at 2. At pi over 4, so angle of pi over 4, remember, root 2 over 2, about 0.75. So about 1.75 in that direction. So probably somewhere here. And we saw with R1, it's going to come around and look like a heart. Something like that. Let's do.
And this is a limason, right? Am I getting that right? A limason?
It's a cardioid, I think, is actually the word for it. Yeah, I think WebAssign actually has you label them. There's limason.
There's limasons, cardioids, like
limnus, I think.
Yeah, could you draw a limason real quick just to show? I think
so. The only difference, so quick break from that. To draw
yeah, thank you, by the way.
I kind of mentioned in notes yesterday, real quick, just to play around if we have something like R is A plus B sine theta. You're going to get 3 different shapes. It's either going to be a heart, where we just get a cusp there. It's going to be, it'll come up and do a full loop. Or it'll just make like a lump, where it'll come down and it won't even touch, and it'll just be like that. This is our cardioid. This is the limason. I don't know how to spell it. I think there's a weird little accent, something somewhere. It's like the weird C. And then this, I think, is a limniscate. So this should be A equal to B. This one, I think, is B bigger than A. And this one is B less than A. Just to think about that, right? It's going to happen whenever sine ends up being negative. So like, if you think about what's going to happen at 3 pi over 2, so if we're pointing downward, it's going to be negative. Sine will give us a negative value. And if this B value is bigger than A, the overall value of R will be negative. So if we're pointing downward and R is negative, we actually go upward here and we make this loop. Whereas if B is less than A, the R value ends up never being negative. So when we're pointing downward, we still have a positive R value. So we're still in a positive direction, or a positive distance in that direction. And so we only make a little lump. Back to our graph. This guy, if you guys have practiced some of these graphs, it is a circle, I believe, with just in the vertical plane here. Because we have 5 sine theta. Sine theta is only going to be negative at 3 pi over 2, or after the angle goes beyond pi. And we can kind of see what's going to happen if we do, let's do one more. So let's do 5 pi over 4. And then maybe we can throw in 3 pi over 2. So maybe 2 more points. What's going to happen with these guys? So here we'll have our 1 minus root 2 over 2. We saw these ones yesterday, and 0 for that guy. For this guy, though, it's essentially just going to alternate between these values. So 5 pi over 4 will give us a negative 5 root 2 over 2. And then 3 pi over 2 is going to give us a negative 5.
Could you move the paper up?
Yeah, sorry about that.
Thank you.
So notice that for R2, this function of 5 sine theta, the only time we have negative radii are when the angle is in the third and fourth quadrant. So essentially what that's going to do is it's going to give us a circle. Let's see. So at pi over 4, we're going to want to plot that 5 times root 2 over 2. So that's going to be 3/4 of 5. So it'll be, let's see, 1, 2, 3, 4, 5. It should be right here. So it's going to come up and hit that value. My scale isn't quite correct on the X's and Y's. And then it'll come up and hit vertical at pi over 2. It'll come back around and then hit 0 again at pi. And then now when the angle, like if the angle is pointing at 5 pi over 4, we just go to negative on the radius, which means we're actually back at this point. So this red should be a circle. Forgive my oblong, wonky looking circle here that I've drawn. But it'll be a circle in the vertical plane, in the top half of the plane. So we're going to have intersection points. We can kind of see where they're at, right? Here's pi over 4, and that's pi. That should be pi over 4 as well. Again, my graphing skills, maybe not the best, but you really just need an overall shape of the curve is the best idea. So maybe we're looking at intersection points somewhere around 5 pi over 6, or pi over 6 and 5 pi over 6. So since we are inside both, we want to find, let's see, let's use this one. The distance sort of closer to the origin inside both. So we're going to find this area here. And let me keep track of time. These problems are starting to take a little longer. We do got to introduce arc length. So we need to find the intersection points and then integrate around for the green and then from 0 to those points for the red, if that makes sense. So first step, with almost anytime you're graphing and finding the areas between two curves, right? We want to find the intersection point. So we're going to have to do that in polar coordinates. So we need 1 plus sine theta equal to 5 sine theta, which means 1 is equal to 4 sine theta. And then 1/4 is equal to sine theta. And unfortunately, since this is APPM, arc sine of 1/4, and it's a disgusting number to work with. Exactly. Thank you, Max. So theta is arc sine of 1/4. And man, my pens are running out. I've been writing so much this semester. We're going to keep it as arc sine of 1/4. Just keep it as that. Don't compute it. And we'll call this actually theta 1. Arc sine of 1/4 is going to give us that angle. What is theta 2 going to be? So we need that same angle over here by symmetry. And it's going to be in the second quadrant. So pi minus arc sine of 1/4. Because those numbers are kind of bad, let's just keep them as they are. And actually, I'm going to write it as theta 1 and theta 2 just to simplify our work and to simplify our setup. So to set this up for you guys, our area is going to be the integral of 1/2 r squared d theta. The problem is, so if we blow this up a little bit, we have our cardioid, our green going around up and above, and then the circle was coming up like this. And so the thing you have to visualize, and it's kind of hard because that angle is fairly small, is that, let's see, so sometimes, like at smaller angles, I guess if we broaden this a little bit more, you can kind of see it. So you'll have to kind of cut it, just as you have to cut areas. If we're doing integrals in rectilinear coordinates, we've seen that sometimes we have to cut the areas into two different pieces. We have to do the same thing for polar coordinates. So the green area, as soon as we cross that intersection, the inside-most function is the cardioid. But in small angles, so between 0 and our theta 1, the outside-most, or excuse me, the inside-most function is the red function, is the circle. Does that make sense? So our green, so our area, let's actually write it. Area is equal to A1 plus A2. So A1 is going to be the area inside curve 1. This will be our green. And then this one's going to be our red. So R1 was our cardioid. R2 was the red. So how do we find A1? 1/2 r squared, so 1 plus sine theta squared d theta. And the bounds are going to be theta 1 to theta 2. The way I would do this, square it out. You're going to have some pieces that are easy. Of course, the linear piece. And actually, if you want, you could go from theta 1 to pi over 2. So just integrate the right half and then multiply it by 2 if you'd like. But you'll have to, of course, square that out. You'll have a constant term, linear term of sine, and then a sine squared, which is the only tricky part to integrate. Integrate all of those, and then you'll have to be evaluating those trig functions on arc trig functions. So the nice thing about keeping it as theta 1, theta 2, it kind of clarifies your writing at the a bit. Then at the end, you'll have some cosines. You'll have evaluations of like cosine evaluated at theta 1. So you'll have to evaluate cosine of arcsine. So remember how to do those way back when we started learning trig integrals. A2, similarly, the best way to probably do A2 by symmetry, since we're looking at the red area, let's just compute the right value and multiply it by 2. So it's going to be 2 times the integral from 0 to theta 1 of R2. So 1/2 5 sine theta squared d theta. So a bit to work through, pretty computationally heavy. It does kind of rehash all the skills. or at least in terms of evaluating trig and arc trig that we've been working on since trig subs, as well as integrating sine squared. Again, we just saw a cosine squared. Remember those double angle formulas, and then just plug and chug with those computations. Any questions on those guys?
If it's inside one and outside the other, wouldn't it be like an area of one minus the other?
Yes. So that was going to look at one of the other examples I was looking at from the book, was if it says inside one curve and outside another, then you've got to do the outside minus the inside. So if it says inside some R1 and outside some other curve, you want to find the intersection points and just essentially subtract them. So the area is going to be 1/2 R1 squared, or I guess we have R2 on the outside, so it'll be R2 squared minus R1 squared d theta. So always do outside minus inside. And then, of course, wherever the intersection points are. Maybe we can see an example like that. Let's try to get through our last topic, at least, arc length, and see one example of that. And then we'll use any free time we have to just do more problems. And we can do a lot more problems tomorrow as well. All right, arc length. In polar. We have the same process. So remember our dx, let's bring that up again, was what? d theta cosine theta minus our sine theta, and dy is d theta sine theta plus our cosine theta. So our arc length, again, still satisfies the Pythagorean theorem. Now we just want to compute and maybe simplify that for our arc length. So let's see what we got. We'll have our dx squared is going to be d theta squared cosine squared minus 2 d theta r cosine theta sine theta, and then plus r squared sine theta squared theta sine squared theta. And then, so this is our dx squared, and then our dy squared, similarly, d theta squared sine squared plus 2 d theta r cosine theta sine theta plus r squared cosine theta. So what's going to happen when we add these two together? The middle terms are going to cancel.
Is it supposed to be a cosine squared theta on the end, or just cosine theta?
Cosine squared, thank you. So then we'll have drd theta squared times cosine squared plus drd theta squared sine squared. If we factor out the drd theta from that, we'll have drd theta squared times the quantity cosine squared plus sine squared, which will just leave us with a factor of drd theta squared. Similarly, when we add those two terms, we factor out the r squared. So it'll be r squared times the quantity sine squared plus cosine squared. And we're just left with an r squared. And I guess I did forget the d thetas here technically. So we would have a d theta squared on both of those. And so it would be all of that d theta squared. But of course, when we take a square root of that, we now find that our ds is square root of, they commonly put the r squared first. And then of course we bring out the d theta. So this is our formula for arc length. All right, so keep that handy. And let's find the length of r equals sine cubed of theta over 3. And they actually give you guys bounds for that. So this is another homework problem that we can get going for you guys. Exact length of the curve is not a very good description, because what's going to happen as theta keeps going, it's going to be infinitely long. And if it's infinitely long, the length is infinite, and we're done. So let's just assume theta is between 0 and 2 pi is our typical range. Oh man, this one's going to be tough. So compute your pieces. R squared sine to the 6th of theta over 3. drd theta is 3 sine squared of theta over 3 times cosine of theta over 3 times 1/3. So of course the 3 and the 1/3 will cancel. Our drd theta squared, squaring all that, sine to the 6th theta over 3 times cosine squared theta over 3. And did I sine to the 4th? On that one. And so what do we want to do? Compute the length 0 to 2 pi square root of r squared plus DRD theta squared. D theta. So setting these up, hopefully not too bad. Hopefully all of these arc length formula problems, if you know the formula for arc length and you're solid with computing derivatives and doing the algebra, setting up the integral, not too hard. Using techniques of integration has been a big theme throughout this whole class. Being able to look at an integral, recognize what to do, what approaches to take, hugely important. What do we want to try? Any ideas?
I mean, there's a trig identity with cosine squared, so then you can get sine squared -1, distribute that sine, so then you get sine 6, so then you can get 2 sine 6 plus sine 4, I think.
Sounds like a good first idea. So especially since we know we kind of have this sine to the 6 over here, and this is 2 powers less. If I could convert these two to sines, we could simplify the sine to the 6 a little better algebraically. Let's check, see what happens. So here we will have 1 minus sine squared. So that'll give us a sine to the 4th theta over 3 minus the sine to the 6th. I guess technically that's a theta over 3 too there. D theta. And now nicely enough, the sine of the 6 actually cancels, so just mind your minus signs with the trig subs and the trig identities. And so what are we left with? Square root of sine of the 4th. And so just an integral of sine squared after that. Any questions? So we've got time for one more, at least maybe getting it started, getting it set up. You guys want to do arc length or areas? You want to see another area one? I think those are a bit harder. Arc length, the nice thing about arc length is it's one curve. You have to have one curve that you're finding the arc length of. So you have to be given that curve, or at least you might be given a rectilinear version of that curve, and it might be better to parameterize it in terms of polar if there's any work to do beforehand. But usually it's simply computing the pieces, computing your r squared, your drd theta, and then squaring that so that you can plug those into the formula. And then from there, it's all algebraic manipulations and techniques of integration. The area ones, you've got to do a little bit more work because you've got to actually graph two functions. You've got to determine their intersection points. And if you screw up the graph, you can kind of screw up the intersection points. Let's see, I had another one written down, and I think the numbers work out a little bit better. Area inside r equals 3 cosine theta, and then outside r equals 1 plus cosine theta. So a little bit different, but these graphs are actually going to look very similar. Let's call them R1 and R2. And this time we'll make this guy green and this guy red. So I'll leave the table and some of the details to graphing to you guys. I'll try to go through it a little quicker now, especially if you guys are getting the hang of this. Maybe you can kind of see how to graph it without making the table and just being able to think through what's going on. And it's really just thinking through the values of the table. When theta is 0, cosine of 0 is 1. So our value is going to be at 3. Then as we rotate around, at pi over 2, we'll be at 0. So at pi over 4, we'll be somewhere up here. And we're going to rotate around and then come back to 0. And just as we saw, 5 sine of theta is a circle, 3 cosine of theta also going to be a circle. It's just going to be in a different part of the plane. And so it'll come down and be a circle here. The red curve, similarly, this should be either a cardioid, a limmason, or a limnoscate. And since the values of the constants are the same, it's going to be a cardioid. You kind of just got to figure out where that hump it is. So again, if we plug in 0, we're going to get 2. At pi over 2, cosine is 0, so we'll be up at 1. Then at pi, cosine is going to be -1. So when we're pointing to the left, we'll be actually at 0. So we'll be at -1 plus that 1. So it's going to look like our cardioid, but the hump, the cusp, is going to be over here on the left. Something like that. Our first step is to find the intersection points. So 3 cosine theta equals 1 plus cosine theta. And now solving these, we'll get 2 cosine theta equals 1. Cosine theta equals 1/2. So theta is going to be pi over 3. And then we're going to need a value in the fourth quadrant as well. Let's actually pick -pi over 3. Since now going from -pi over 3 to pi over 3 gives us this counterclockwise motion starting at a negative angle up through 0 to positive pi over 3. And what do we want? So we want inside the green and outside the red. So the area we want is going to be this area. So be careful with the insides and outsides. Like in the last problem, on the homework problem, it says inside both, meaning we want just that area inside both of them. This one we want outside of the red, inside of the green. So our area is going to be -pi over 3 to pi over 3. 1/2 is going to be the outside area. So it'll be 3 cosine theta squared, and then we subtract off the inside area. 1 plus cosine theta squared. So again, you'll have the trig integral to do. The other problem is pretty much similarly. Don't get thrown off by the bounds in that homework problem. Keep it as theta 1, theta 2. Focusing focus on doing the integral correctly. Of course, remember the integral setup was a little different from this. We had to do it in pieces. Do the integrals correctly. Then at the end, do the trig evaluations. You'll have trig evaluated on inverse trig functions. So just do the one piece at a time in terms of the calculations, so you won't get brain fried doing that one. All right, any questions?